Ancient tectonic patterns may hold the key to finding critical rare earth elements. A groundbreaking study has revealed that the blueprints for the world's most vital mineral deposits were laid down billions of years ago by ancient tectonic movements. By identifying a direct link between prehistoric subduction zones and modern-day rare earth element (RE) deposits, researchers have provided a new roadmap for locating the materials essential to the green energy transition. The search for green tech essentials rare earth elements. A group of 17 metallic elements, including yttrium and scandium, are the silent engines of modern technology. They are indispensable for electric vehicle (EV), batteries, wind turbine, magnets, smartphones, and high-tech electronics. Despite their importance, finding deposits large and concentrated enough to be commercially viable is notoriously difficult. Until now, much of the search was directed toward mantle plumes, massive columns of molten rock rising from the Earth's core. However, this new research suggests we may have been looking in the wrong places. A new geological model. The fertilized mantle, published in Science Advances, the study led by Professor Carl Spandler of Adelaide University, challenges the dominance of the mantle plume theory. Instead, the research points toward ancient subduction zones, areas where one tectonic plate dives beneath another, as the primary architects of RE deposits. The process works through a long-term fertilization of the Earth's mantle. Subduction. As a tectonic plate sinks, it releases fluids and halogens, such as fluorine and chlorine, into the mantle above it. Fertilization. These substances react with mantle rocks, like peridotite, creating enriched, fertilized regions. Storage. Remarkably, these enriched zones can remain stable for millions or even billions of years. Melting. Eventually, these zones melt to form alkaline and carbonatite magmas, which carry the rare earth elements toward the surface to form mineral deposits. This research shows that the ingredients for these critical mineral deposits were put in place many millions to even billions of years ago, says lead author Carl Spandler. Why the time lag matters. One of the most surprising findings is the massive delay between the initial tectonic activity and the formation of the actual deposit. The Earth's mantle acts as a massive, slow-moving storage unit. The data shows a staggering correlation. 67% of known alkaline/carbonatite magma blobs sit atop fertilized mantle. 72% of known rare earth deposits are located above these regions. For older, higher-grade deposits, those over 540 million years old, the correlation jumps to 92%. This suggests that the most valuable and largest deposits are often the result of ancient geological processes that have been waiting for the right conditions, such as continental stretching or pressure changes, to finally rise to the surface. A targeted strategy for future exploration for mining companies and governments. This discovery transforms the exploration process from a needle in a haystack search into a targeted geological investigation. Rather than scanning vast, random areas, exploration can now focus on ancient subduction zones identified through tectonic modeling, regions where multiple fertilized mantle areas overlap, which tend to host more significant deposits, stable crust and upper mantle regions where low-temperature magmas are more likely to form. Conclusion: by shifting the focus from deep mantle plumes to ancient tectonic fertilization zones, scientists have provided a powerful new tool for locating the minerals required to power the future of global technology and renewable energy.